Hello everyone, welcome to week 9. We're going to have another exciting day today. We're going to implement particles in a modern OpenGL framework. In order to do that, we have some files we need to download from Blackboard. If you get the package, you'll find 2 textures and a few source files. Let's take those into our project. Bring those into here, then we can move our textures into the actual textures folder. Now we don't need to play around with that anymore, but let's bring those files into our solution. So I'm going to add an existing item. That's going to be our particle effect as well as our random. And I can add all of them here and then just move the CPP files down to the source files folder. Now normally I wouldn't want to give out code. And that is still the case, but I made an exception here because of the fact that we've already covered this material last semester, and there's no sense going over it again. So I'll just introduce you to the files quickly. We have a particle effect, which has some of the some similar code to what we worked with last semester with our locomotion and our updating and generation and our deletion of particles. And then we have the random header, which allows us, mostly the particle system, to generate random numbers in order to distribute the particles. So things are a little bit different in the particle effect this time. The particle list struct here is now what holds the bulk of the data for particles. So we still have positions, velocities, sizes, and alphas, and we still keep track of each particle's age individually and their maximum lifetimes. But now they're not in standard vector objects anymore, and they're all split up like this. Instead of there being a particle class that has one position and one velocity, now we have just one entire list that stores all the particles in this format. And the reason that we're doing this, as we'll see later, is so that we can more easily send this data to OpenGL. So essentially the idea is every single one of these pointers points to a dynamically allocated array of particles, and if we were to say index into positions at 10, then we could find the corresponding value of that particle for velocities by also going to index 10. And then index 10 for size, index 10 for alpha, ages, and lifetimes would be all the information for that particular particle. The reason, again, that we've set it up this way now is in order to interface better with OpenGL and also to provide some performance optimizations, as we'll see in the CPP. So we'll take a look real quickly in particle effect.cpp. The init function now, as you can see, takes the max particles and creates those dynamically allocated arrays ready to go. So there's no more pushback and popback of particles. There's no more erasing of particles in real time, shrinking and growing the list. Now we just create an entire pool of all the particles that can possibly exist, and we only draw as many as we need to, even if the memory space is there for more. So the update function you've seen from last semester, if we don't have too many particles, if we still have room in our arrays, but also we have the number to spawn this frame, then we go through, we generate a new particle, we pick up the initial data. Some of it is determined by these random ranges, and then what we do here is we increment this counter, which means that because num particles is going to be 1 more on the next time around, we'll essentially be writing a new particle the next time it gets generated. And this also tells us how many we need to draw and what our current amount is. Now before I move forward, I do want to make one note here that all of these ranges, or some of them anyways, are using vector 2s for their values. And this is something you'll see relatively often in the industry. If we go down to the actual data in the particle effect class itself, we have these ranges here, which are intended to supply a minimum and maximum extent range for a particular value that can exist. So when we generate the exposition of the particle, really we want it to be between -10, and +10. And one way to neatly group together that range is in a variable that stores exactly two values, which is a vec2. So sometimes you'll see vector objects, particularly vec2, used for ranges. So don't get caught off guard by that. And so here, when we specify range lifetime.x, really we're talking about the minimum extent possible, and then the y value is the maximum extent possible. Random range f picks a value between those two, returns it to the corresponding parameter that we're setting. So that's going on there. What else has changed has been the removal of particles. It's now been made much more efficient, and this will just work. So if you don't want to worry about it, you don't have to worry about it, but I would recommend you give this code a good read. Reading code is in fact a skill that is very important to develop, and the reason that it's a skill is because right now a lot of you are probably feeling a little bit intimidated that these changes have happened underneath your nose. And so, of course, the only way to get over that intimidation is to get used to reading new code that you haven't seen before. So absolutely, I recommend you take a close look at this code when you have some time. Pause the video if you want. But let's talk about what's happened here. So instead of erasing an element in our array when a particle is dead, we instead do something a little bit sneaky. So let's say let's say a particle halfway in the middle of our array has died. It's run out of life. Normally, with the std vector approach, we would have called erase on that element, which would have removed it from memory and then shifted down everything after it -1 in the array. So it would have taken everything, shifted it down, and of course the standard vector going and moving everything would have taken a long time. Imagine erasing the very first element of a 1000 length array. The standard vector would spend a lot of time needlessly moving that whole array down just so that there's no empty spots. What we can do something else instead. What we can do is we can say, okay, this particle's dead, but we don't want to have that hole in the array, so let's just copy the very last existing particle, so the rightmost one. So if we're talking about the case with erasing the first element in a list of 1000, so I would be equal to 0, and we actually copy over the 1000th particle into slot 0. And so instead of moving everything back, we just take the very last element and we fill in the hole. And then, of course, our num_particles list, or our num_particles counter goes down by just 1, since technically the end of the array has shifted down 1. So we have virtually the same effect because it doesn't matter what order the particles are in, but we save so much time in dealing with the standard vector and making it shift everything around. So I feel that this change is worthy to note, and I hope some of you like the idea of this and play around with it in your own engines. But the rest here is just our basic physics calculations, determining interpolation value based on lifetime, changing the alpha and size of the particular particle. So that we've seen before. Then we have our render function, which of course we're going to fill in today, and we're going to have to do some things to the initialization as well. But you should be familiar with the ideas that are here for the particles. So in order to get today's stuff working, let's start by making a change to the shader program class. As we saw in the tutorial, we're going to need a new type of shader, the geometry shader, in order to get our particle effect. Working. So let's go to shader program. Now we have the load here. I'm going to copy this load function, make a new one that also takes a standard string geom file. And so with this overloaded function of the same name, I've given the user the option to load a shader with both just the regular shaders, to load a program with both just the fragment. Whoa. So with this overloaded function, I've given the user the option to load a program through just a vertex and fragment shader, so none of the existing code will break, but now you have the added option of using the geometry shader. So let's take this function definition into our CPP, go down and add it right after. And so, as we'll see, it's actually very easy to load a geometry shader. It is basically treated just like any other shader that we've already loaded in, so we can use a lot of the existing code. So let's copy the existing function, bring it down into here, go to the top, and make the changes we need to. So first of all, we're going to want geometry shader variable, right? We'll fill that into the header file in just a second. But as you might be able to imagine, to make one of those, we'll call create shader. And we'll specify the geometry shader value here. So let's take this into the header file. Can create a new GLUint geometry shader equals 0. Have some vertical spacing there to make things easier to read. Now we can duplicate this this block here that loads in the text and sends it to OpenGL. So let's take the file, load that one this time, and then instead of targeting the fragment shader, we're going to target the geometry shader here. Next, we have these blocks that compile each shader. Luckily, we wrote this function to be generic, so we can just pass in our geometry shader here. If something goes wrong, we want to output the shader log for the geometry shader. And then here, we specify in the string, geometry shader failed to compile. Last thing to do here is officially attach it to the program object using, again, its handle, and we're done. Geometry shaders are now available to us in our framework. Binding the programs doesn't change, sending uniforms doesn't change, no other function at all is needed, just adding an extra integer here. And much of that is also true for tessellation shaders as well. So now that that's done, let's really dig into the particle effect class. So that's going to be the bulk of the work today. So first things first, we're going to want to upgrade this to use our own texture class. So we're going to include texture.h here. Not going to be using the sprite-lib functionality anymore. Now that we have a texture, we're going to want to yeah, there we go. We're going to want to create the variable in here so that we have somewhere to load it. Then we're going to create two GLUint handles, one for a VAO and then one for a VBO. So we know that we're going to need a VAO and a VBO to some extent, right? We're using modern OpenGL, but how exactly is that going to work? Well, what we're going to do is we're going to, as you've seen in the init function, still have this memory handled and managed on the CPU, but after we've made changes to it, we're going to upload the state of these arrays into OpenGL, into this VBO, and then when that VAO is rendered, it'll be able to use the existing data as vertex attributes. So we're going to be sending through data into vertex attributes that's not UV coordinates nor normals. So it's going to be different than what we've done before, but like we've mentioned many times, Andrew and I, everything is just data. OpenGL doesn't care what you send through. You can store whatever you want in these VBOs. So we're going to be putting size and alpha as well as positions in them today. Now, since we want to have 3 of these things, we're going to use 3 VBOs, not just one. So I'm going to write 2 more. The next one is going to specify the sizes of each particle, and the last one is going to specify the current alpha value for each particle. So of course, it would be possible to actually upload all of this data into one VBO, but we're not going to be doing that. For sake of simplicity, we're going to keep them separate. So all of these should be initialized to 0. And we can take a look at the initialization function itself. So let's head over to particleEffect.cpp. Right at the top, I'm going to add something before we need it. Let's add that buffer offset define we always need to use. Hopefully it doesn't warrant explanation anymore. Moving down, top to bottom, particle effect is going to need a couple new things. The destructor, sorry. If our VAO exists, I should say if it is not equal to GL none, then I will GL delete it. That is delete vertex array, yeah. Delete one of them and take our VAO. Perfect. Then we will write similar code for our VBOs. Why is it fighting me? There we go, position. Delete one buffer. VBO position. You get the idea. Delete the size as well as the alpha. So now our destructor is a little bit safer. Let's go down to init. Bunch is going to change here. So first of all, this incoming texture file we're going to want to load. So let's make sure it doesn't fail. And let's texture dot load texture file, as you might imagine. If it doesn't work, then we're inside this if statement, and we're going to want to return false and not continue. However, if it did work, we can go ahead and save the values of our max particle and our spawn rate. We can create the arrays as we have here, but now we're also going to need to set up the same kind of memory space on the GPU. So we're going to want to set up our GPU memory. So first things first, I'm going to gen our vertex array, which is going to want one of those, specify our VAO. We're going to want to bind it. Pardon me, we're going to bind vertex array. Now we're going to want to enable the slots that we're going to be using, and it's going to look similar to the way we did it in mesh.cpp. In fact, a lot of this code will. So remember, Same kind of format, generate our stuff, bind the VAO so it starts remembering state, and then we can specify our buffers and upload any data to them as necessary. So I suppose in interest of being exactly the same, we'll generate our buffers as well. So gen buffers, I'm going to gen 1 at our VBO position, and also one for our size and alpha. Then we can bind our VAO and start enabling our client states, which is just a fancy way to say that, oh sorry, it's not called that anymore, that's the old version of the function. We're going to be enabling our vertex attrib arrays. Client state here is the old way to do it. So we're going to enable vertex attrib array. We're going to want slot 0, whoops, slot 1 and slot 2. So if we comment these, first one is going to be for vertices. Second one we're going to use for sizes. Third one we're going to use for alphas. So let's get to each of these individual buffers. So we're going to bind a buffer. We're going to bind as an array buffer, a standard buffer to hold data. We're going to bind our first one, VBO positions. Now this one's going to be very familiar to us because we've created buffers that are vector 3s before. So we're going to call our buffer data. Our target is going to again be array buffer. We're going to, as the size, take the size of a vec3. Right? Every single element in this array, in this buffer, will be a vec3, and that's going to be multiplied by the number of elements that we actually have, which is our max particles, right? Now we create the size and the entire pool of the maximum amount so that we never have to resize. And the same is true for the GPU. We certainly don't want the GPU to be resizing this array as things go along. That would be awfully slow. So after that's done, specify the data, which is actually going to be null. We don't want to upload any data yet. That's going to be done on a per frame basis. And for the last part, we're going to specify, as a hint for how we're using this buffer, we're going to specify dynamic draw this time, instead of, if you remember what we used in mesh.cpp, I think it was static draw, yeah. So static draw implies that you're going to be using this buffer to draw, and you're not going to be changing it, or you're going to be changing it very infrequently. Now, things are a little bit different this time around. We're going to be uploading this buffer every single frame with the most up-to-date particles. So we're going to want to specify dynamic in the middle. Now, OpenGL is free to ignore what you put in here at the end, but it's a hint which tells OpenGL how you intend to use the buffer, and depending on what computer you're running on, it might be able to place this buffer in a more advantageous position in memory to better upload from the CPU and get things done faster. So it's always good to use the right hint there. If not for performance, then as a hint to whoever's reading your code as to how you intend to use that buffer yourself. So let's bind our next one, our VBO for size. Why not? And we're going to be using uniform scale. So when we send our data, we're going to just need one float and not 2 or 3 for each axis. So we're going to bind to array buffer again, and our size is going to be float times max particles, not uploading data yet, so again null, and then GL dynamic draw. Perfect. Next one, GL bind buffer, GL array buffer, VBO alpha. Let's just get all of these out of the way and then we'll move to the next step. Array buffer. Same idea here, right? It's going to be exactly the same. Our alpha value for the color is going to be stored as a float. So 1 per particle, just one float. Null, and then dynamic draw as our hint. So now that we've created these buffers, we want to properly associate them with these slots that we've enabled up here. So while the current buffer is still bound, I'm going to want to call GL vertex attrib pointer. And again, just like in the mesh, this associates the current VBO with the slots so that that is actually the data that is being fed into that location once you get to the point where you're talking about the vertex shader. So the first parameter here, I'm going to explicitly cast to a GLU int, is going to be the slot we're referring to. We're talking about positions, so we're going to be in slot 0. Next is the size, which is not the byte size, but instead how many raw data types are in here. And there's 3 floats, so the raw data type is a float. And there's 3 of them, so we're going to say 3, then we're going to say GL float. We want to specify false next because we don't want OpenGL to be touching our data and normalizing it. Our stride is going to be 0 because we're not putting this data isn't spaced out to get to the next element. It simply has to move over one index. And then lastly, we have the variable that's asking us how far from the beginning of the array does this data actually start. Does it start in the middle? Does it start 3 points down? Sometimes at the very start you'll have a little bit of extra data specifying certain global things. We're not going to be doing that, right? Our buffer starts right at the start. Whoops. So let's make another one of these for the size. Now be very careful to update all these values. This is going to be slot 1 now. Still a raw type of float, but now there's going to be only one of them per element, and everything else is the same. Then for our last one, our alpha, everything is the same except the slot gets bound to 2. After all that's done, we can bind buffer GL none to make sure nothing is still bound. We can do the same for our vertex attrib array. Just copy paste a few times here. And now everything's being unbound. So we have everything ready to go. Of course, the question now is how are we actually going to get this data into OpenGL so that you can use it? Well, let's take a look at the update function. This is where we're going to be adding this. After the particles have been updated, so once a frame, we're going to update OpenGL on the changes. We're going to tell it what's happened. So going to be doing something a little bit new here since we've never updated a VBO after the fact, but this is going to be a good experience. So we're going to need to bind each one. So let's start with our positions because position is something that we're used to working with. So we'll bind our array buffer VBO position. Then we're going to call not buffer data, but buffer subdata. There's a very important reason for that, a very important performance reason for that. If we were to call buffer data, then we would actually reallocate the entire array. That is to say, the GPU memory holding our array would be deleted, and a new one would be created of the size that we specify. Buffer subdata updates the data in an existing array, and it's called subdata because you can actually just update a small subset of it as you need to. This is absolutely perfect for us because if we're only working with 100 out of our potential 1000 particles, then we can call subdata on just the first 100 and just update the data space that we need instead of taking the time to overwrite all of the memory needlessly on the GPU. So there's lots of good reasons to be using this function. Although the actual parameter list is going to be I feel very self-explanatory. So we're going to want to specify the buffer type, which is just a standard buffer, the offset, which is where in the array do we want to start uploading. We're going to start at the beginning of 0. The size, how much do we want to actually update? Well, depends how many particles we have, right? So it's going to be vector 3 is our type, and that's going to be multiplied by not max particles, but actually we can get away with just uploading this value, our current particle count. So if it's 0, then actually nothing will even happen here, and the call will return. And lastly, of course, is the pointer to the actual data to be uploaded, which we're going to get from our particles dot positions at index 0. We're going to get the address of that. Now here exactly at the end is why we decided to use arrays like this for the particle list. I know it seems a little bit weird to do it this way instead of just having a struct that represents one particle and then having an array of that, but now you can see that having all the positions continuously in memory, as well as all the velocities and the sizes, makes it very, very easy to upload the data to OpenGL. So that's why we did that. Let's go ahead and bind the next buffer. Array buffer VBO alpha, or actually if I want to stay in the order of things that we did here, I'll do size next. Let's go back to size. I'm going to call the same function, GL buffer subdata, GL array buffer, start at the beginning of this space in memory. How much do I want to upload to that location? Well, the size of a float, because we're just uploading the float sizes, times the number of current particles. Then we grab that data from our particles dot size array. Simple, right? Let's bind our last one. Our array buffer VBO alphas. Get our buffer subdata. Right, we're basically mirroring the code at this point. Size of float times num current particles, and for this last one, for alphas, we're going to pull from, that's right, you guessed it, the alpha array. And then we end off by unbinding the array buffer with binding GL none. Let's remove this space here. So here we go. That's actually all it took. And now all the data is uploaded and updated, and only the amount that we actually need for the current frame. So this is short of actually doing all the particle updates and everything on the GPU, this is as efficient as you're going to get. And you're going to find that using this system, you can push a heck of a lot of particles, especially when you take a look at the brilliant render function we're about to write. It's going to be awesome. So let's get right to it. First things first, we want to bind our texture. So let's take that, let's bind it. Let's work with a little bit of symmetry here so that we don't forget. We're going to unbind the texture later at the end. Then what do we want to do? These are particles, so we're going to want to enable blending so that the parts of the texture that have alpha can actually be seen through. And then on the opposite side here, I'm going to disable that. Now, when we enable blending, I'm going to want to specifically set the blend function, which is going to specify how the new vertex, how the new fragment that is output from our fragment shader is going to mix and blend with the one that is already in the FBO or the back buffer. Right, so OpenGL doesn't necessarily want to assume anything, right? It has an existing pixel and you want to shade something over it, and it wants to ask you, how do you want that behavior to take place, right? How should I make that mix occur? There's actually a lot of different ways, and a lot of these tie into the different blend functions that you'll have in Photoshop as well, like multiply and screen or subtract, or you could just overwrite. Even if there is alpha, you can overwrite what's in the destination buffer in the back buffer. But we're going to specify the one that's most intuitive, the one that if I were to tell you we're using transparent blending and we're using objects with alpha values, this would be what you would imagine. So in order to get that effect, which is actually not the default, we're going to specify source alpha as our first parameter here, and then we're going to specify 1 minus source alpha as our second parameter. I recommend Googling this function, checking out the page for it, and the detailed description if you're curious to know more. So after that's done, we're going to change one more state. We're going to set the depth mask to false. Sorry, not that false, GL false. It would probably still work, but let's be consistent. And then at the end, we set it to true. Depth mask disables or enables depth testing. So, oh, sorry, pardon me, that's not true. Depth mask disables or enables the ability for a render to write to the depth buffer. So if I wanted an object not to occlude other objects, then I would simply stop it from being able to write to the depth buffer, and then the depth values wouldn't be there for that object. It would have popped up in the scene as though it was depth tested and everything, but anything rendered after that won't see that object there. So this is really useful for particles because of the fact that particles have alpha values. So if we render particles, because they're transparent, like with anything else in 3D graphics rendering, transparent objects need to be rendered from the furthest in distance, slowly stepping towards the camera. And we don't want to take the time to sort thousands of particles from furthest to closest to camera. So instead, we're just going to say, you can't write to the depth buffer. So even if a particle that is very close to the camera and basically covers our whole screen is rendered first, that won't stop all the other particles from rendering behind it down into the scene. Now, of course, this does have some disadvantages, such as the fact that we're not going to be able to use these particles to cast shadows, but most of the time, you don't want to do that anyways. So that's why we're disabling the depth mask there. In terms of rendering, we're going to want to bind our vertex array, or VAO. Then we're going to draw arrays. We're going to use GL points this time, right? Because the geometry shader will take the work of transforming them into quads, as we'll see in a second. We're going to render from point 0, and we're going to render num current particles. Then we unbind the VAO. And that is it. That's how tight the render loop happens. And thousands of particles can be drawn in one call. And that's one of the reasons that this modern OpenGL implementation of the particle system is going to be so absolutely lightning fast. All of them are going to be pushed through, and all of them are still going to have independent positions, sizes, and alphas. So keep in mind here that the third parameter, numCurrent particles, is going to make sure that we don't overstep the bounds of how much data we've updated. We've only updated from 0 to numCurrent particles, and that's only the amount of that we're going to draw. So it doesn't matter that we didn't update the rest of these buffers. So in order to get this working, we're going to need to, of course, write the shaders. So we can imagine now the data that's going into the shaders because we've set it up. So let's see how we can write these shaders to actually do the trick. So let's create a new folder in our shaders assets. Call it particles. I'm going to create 3 text documents here. We're going to call them billboard. Going to make one dot vert. Going to make one a dot frag, and the last one I'm going to make a dot geom, G-E-O-M, and that's an extension that will be picked up by the end shader extension. So the plugin, that is. So now let's create a matching folder in here in our Visual Studios project. So particles, did I have an S? Yes, I did. Particles, then we'll add existing items, shaders, particles, those guys. Let's bring them in. Start with our vert. Our version is going to, of course, be for 20. Going to have a couple uniforms here. Going to have our U model. Going to have a uniform, our U view. And now we're not going to have a projection matrix. So remember that the geometry shader that's going to happen next is going to have the output of whatever this vertex shader spits out. And remember from how we saw in class, the view space is really where we want to work in the geometry shader. So we're going to wait and apply the projection matrix in the geometry shader rather than the vertex shader. And that's going to allow us to apply the billboarding effect. So we're not going to have it here. So we're going to have our layout, location 0, which corresponds to our slot 0, which we want our positions in. So that's going to be coming in as a vec3. We can call that invert. Specify another layout location 1 here. It's going to be floats this time, right? We've never seen vertex attributes that are floats, but of course it's possible. That's going to be our sizes. Then our last layout, location equals 2. It's going to be our float in alpha. Now what are we going to want to give to the geometry shader? Well, we're going to want to pass through the size. We're going to want to pass through the alpha so that the geometry shader can do its thing. And then of course we're going to transform the vertex using the matrices. So our main function is going to be rather simple. We write to GL position, capital P, equals U view times U model times, let's cast this guy up to a vec4 so we can multiply it by the matrices, invert, then append that 1 at the end there. Our size is going to just get the value of in size. These are not relevant to us right now, but they will be in the geometry shader. So now that these are done, let's see exactly what the geometry shader is going to look like. So we'll open that. Geometry shader is also going to start with version. It's going to be 420. Then we're going to be receiving from the vertex shader a size, and we're also going to be receiving an alpha. So just as though we were passing something from a vertex to a fragment shader, you have the in variables corresponding with the out variables of the previous step. The only difference now is that we've added that extra step in the middle, which is the geometry shader. So instead of vertex outputting direct to fragment, now the vertex is outputting to this geometry shader, and it'll be the geometry shader's responsibility to output variables that the fragment shader is expecting. So we have these now, but there's a bit of a catch. We have to specify them as arrays, because as far as this geometry shader is concerned, the incoming types might be, there might be more than one, because we might be using triangles or something that has multiple vertices. In our case, we know that we won't be, but it still has to be specified like that. It's just going to act as an array with one element. So our input type is going to be the type that we're rendering with, which is points. And our output type is going to be, we want to output a triangle, or rather a quad. Now, we can't specify triangle, we're only allowed to specify triangle strip, which is essentially you write a triangle and then the next vertex that you create is linked with the previous two to create the next triangle. So you can kind of create this fan as you go along, and it saves you time not having to redundantly state two triangles over and over again each time, assuming that the triangles are in fact connected. Now we're going to be using that, and you'll see how it makes our life a little bit easier. And our max vertices, well, we know for sure that we want to turn this point into a quad. So we're going to need 4 vertices. So output data here is going to be to our fragment shader. Our fragment shader is going to want a text coordinate, that's for sure. And it's also going to want a an alpha. We have to give it a different name though because we have this one here, so we'll call it frag alpha. Then our uniform variable is going to be just 1, our projection matrix. And next we have our main function. So we're not going to be outputting the size to the fragment shader because it's not going to be concerned about that. The size is going to be taken into consideration here when we transform this input point from a point to a quad, and the size is going to determine how large we make this quad. So let's start by grabbing a variable that we can work with, which is going to be our current position, and we can grab that from a built-in variable called glin. We're going to grab the first element, the only one that'll exist in our case, and we're going to ask it for gl position dot xyz. So now that we have that, we can start creating our vertices. So we're going to create our first one, which means that we're going to set up all our data the way we want it before calling, if we jump a little ahead, emit vertex. So this function here is going to be what registers the vertex as ready to go down the pipeline. So essentially we get all of these output variables in the state that we want. We emit vertex, then we can get them all in the state that we want for the next one, emit vertex, and in that fashion we can output as many things as we want even though we only have one set of output variables. So our out alpha is going to be equal to our input alpha. Our text coord is going to be equal to vec2. Now if we start at if we imagine this as being the bottom left hand vertex, we can hard code our texture coordinate right here as 0, 0. And as you'll see for the other vertices, it'll be 1, 0, 0, 1, and 1, 1. So we don't even need texture coordinates to come from the GPU memory, from VBOs. We can actually generate those values right here. It's awesome. Let's prepare the actual position that we want to write. That's going to be our U projection. Whoops, it's not that big. U proj multiplied by a vec4, where the first two elements are going to be x and y, but those are going to be offset by something. They're going to be offset by negative 0.5 in one direction, 0.5 in the other direction, and then that there is scaled by our incoming size at 0. So this here is just for our first XYZ coordinates, and because we know that we're in view space, this is going to guaranteed offset these coordinates in such a way that they're billboarded. They're never going to be changing on the z-axis in order to give the this quad perspective. So now that that's being done, we can fill in our z-coordinate, which is just our incoming z. We don't want to change that, as I just mentioned. And then our w component remains as 1. And vertex is emitted. So we just need to do this 4 times. So let's copy a new one. We don't actually need to state again that frag alpha is equal to alpha 0, but I'll leave it there for sake of being more explicit. Then text coordinate is now going to change. We're going to move to the right and generate the bottom right hand corner this time. So we're going to have that turn into 1, but also here our negative is going to change. And I just realized that would have been a nasty bug. Let's change that negative up here. Since we're moving to the bottom left hand corner, make sure both of those are negative. And then here we're moving down on just the Y. So we can have that be the offset. Then we're done. Next one. Let's do our 0, our 0, 1, which means that we're going to have the negative on the left hand side here. Then our last one, and at this point keep in mind these will generate a triangle, and then because we're using a strip, when we specify the fourth vertex, the last 3 will generate the second triangle. So it's very nice that we don't have to specify these middle 2 sections twice. And this last one will have, of course, both the positive components. And now that we are ready and done forming our triangle strip, we need to register the entire primitive. So above just emitting vertices, we're going to emit the entire primitive to finish this off. And now, as if by magic, every single point that is actually going to be rendered by this particle effect will be expanded into a quad based on the parameters that are being updated every frame, that are being randomly generated, all this awesome stuff. So last is our fragment shader, which is relatively uninteresting as far as fragment shader goes. Going to be version 420, uniform, sampler 2D, utext. As we're used to, we're going to want to read from a texture. Now, what's coming out of the geometry shader? Well, we're going to have one vec2 text coord, which of course is interpolated as well. So if we have fragments in the middle of the shapes, we're going to have all the different ranges of text coordinates that can exist. Then we're going to have our float frag alpha, which matches the name of the output in the geometry. And then of course we specify, because we are in a fragment shader, the out color. Specify a vec4 because we do indeed need the alpha channel for sure. Our int main is going to pardon me, our in main is going to take our out color, and that's going to be equal to a texture read where the parameter is the texture we want at the coordinate we are given. We want to make sure that we grab all 4 channels, and then in order to incorporate the alpha that's given to us, we can also multiply by the incoming float alpha here. And so even if the texture has full alpha, this being 0 will override what's in the texture, and if the texture has a see-through component that's 0, it'll override because it's 0 being multiplied by something else, it'll override whatever frag alpha might be, even if it's 1. And that's it. We are done with our billboard section of shaders. So let's go into our game and let's plop one of these things in. Let's have some fun now. So let's go down to entities. Oh, actually, let's not yet. Let's go up to the top and include our new particle effect.h. Then we can go down to entities. Let's create a new particle effect. Let's create a sparkle effect around the sword. That'll give it a little bit of an interesting dynamic feel as things are happening, and will kind of hint to the player that, ooh, something's going on at that sword. I probably really want to go get it. So we'll implement a second effect later. In fact, let's just do them both at once. Let's get a fog effect as well. And now that fog isn't going to be the regular fog that we saw in class, but it's going to be some shaders along the ground to add a little bit of mist instead of just having this flat ground that just exists, there's going to be a little bit of action on top of it. These subtle fog quads moving around, giving it a bit of life, making it feel a little bit more swampy. Let's take this to our game.cpp, and oh, I'm sorry, we'll actually need to also create the shader program for it. Get the shader program. Let's get our billboard, and let's load that guy first. Let's go into game.cpp. You can load it at the end. That's our last shader there. I'll copy that block and use billboard. Now the difference is we're going to actually have 3 files that we specify here, and so I'll put them all on a separate line because we're going to run out of space. Pardon me. So our shader is going to load shaders, particles, billboard.vert. It's also going to load the .frag component, and it's going to load the geom component. Now that we've gone this far, I'm going to breakpoint here. I'd like to build the project, give it a run, just to see that the shader compiles, right? Why take on all the errors at once? Hey guys, I'm back. So it turns out, whoever designed this recording software decided it was a terrific idea to make the hotkeys for stopping a recording the same hotkeys that Visual Studio uses to step breakpoints. So that was a nasty surprise, but of course I'm sure they weren't deciding on those keys just to annoy Visual Studio developers. But I've disabled them, so let's move on. So we're here trying to figure out if our billboard is loading, and it is not. So let's find out why. Syntax error, oh, just something small. Vertex shader, line 3 and line 4. Let's check that out. Some small mistakes. Line 3 and 4. Oh, wow. I didn't specify that these uniforms are, of course, 4x4 matrices. Quite silly of me, and quite observant of many of you, I'm sure, that noticed that before I did. Okay, and there we go. And the rest is good. So, small little catch. That won't scare us later. Let's go ahead and get further down in this file and start thinking about loading our particle effects themselves. And now, because the particle effects have, let's go right to the bottom, let's go right here. Because they have all of these range variables as public, as you can see here, we're going to have a lot to play with, which in the last semester I kept hard-coded because I wanted you to go ahead and expose those variables yourself. And I know some of you did, and this time, you know, I want to really have some fun and make some cool effects, so I left them exposed for all of you. So let's load our first effect. So if not fog effect dot init, our first variable is going to be path to the texture, which is going to be assets textures with an S, fog.png, followed by the max amount of particles. We're going to want a lot of these. Go for 1200, and then the rate, which will be a per frame basis, I'll leave at 10. Now, if that doesn't work, I'll output that, not the FBO, but rather the particle effect failed to initialize. Let's start playing with some of these values. So let's set our lerp alpha, which is the start alpha, which we'll leave as 0.1, and then the final alpha as the effect reaches, sorry, that should have a dot set because that's a vector2 dot set. So when the particle is created, it'll have the alpha on the left, and then as it reaches the end of its lifetime, it'll reach the 0 on the right. So let's have, what's next? Let's do lerp size dot set. These I'll start at 0, 0. So they grow from nothing to about 5, so that there's not, so that there isn't a weird pop in existence, but rather it grows from nothingness and starts appearing, and so it's smooth. Fog effect dot range lifetime dot set. Let's see, these we can have stay for a while. 8 to 20 seconds. Now, I'm not pulling all of these numbers off the top of my head. I've been playing with these all day and I have something that looks decent now. So I'm going to just be telling you what I've used. But of course, you can absolutely play around with these and make a ton of new effects. Velocity, we're not going to want these to move too fast. It's just a swampy kind of fog. Fog effect dot range X. Where do we want this to spawn? Well, I've determined that about 25 in each direction is the size of our little scene. So we go from -25 to +25. The same is true for the Z, so I'll do the Z here. But the Y, we don't want to do that because our Y exists on the 0, our scene exists on 0Y going upwards. Pardon me. Which means that -25 would actually put a lot of things below the ground where we can't see it. So instead, let's do 0.2. And let's go up to something like 0.3. We really just want it to hover around the top of the ground. Fog effect. Oh, that's actually the last of them. So that's our fog. Let's copy this. Let's paste it, and let's set up our sparkly sparkles. So we place all of this with sparkles and replace the fog here with sparkle. The values are going to be different in the initialization as well. These sparkles are going to appear around the sword, and we certainly don't want this many of them. We just want four maximum at a time, right? You don't want sparkles to be overkill. It's just a little bit of a highlight every now and then. So we spawn 1 per frame, and we allow 4 to exist at any point in time. Our lerp alpha, we can start a little brighter this time. 0.5 going to 0, so it disappears smoothly. We can start the size at 0 and then go to 1. Sparkles should live out their life a lot faster so that they have a little bit more action going on and interpolate faster, so 1 to 1.5. Velocity, I'll slow down a little bit, 0.25 and then 0.33. Range X, I want to really just set as an area around the sword for all of these. So I'm going to have -1.5 to 1.5, which is basically the center of the map where the sword is. The height I'm going to raise up to 2, going to 7.5, which will cover the height of the sword, and then also -0.5 and 1.5 positive for range Z. So now these are created. Let's also make sure that they will in fact compile. Then when we run, we're ready to go. Then we'll take a look at end site. So that one compiled, and that one compiled just fine. Cool. Let's go to our update loop. Anywhere in here after we get our delta time, we can take our fog effect and we can update it, passing that delta time in there. Then our sparkle effect as well. Update delta time. Boom. Now the last part is rendering it. So let's take a look at where that's going to happen. So first things first, here we actually have the compute shadow map. And we don't want to render the particles here. We're not intending to shadow these particles. You could try to if you'd like. That could work out pretty cool. But we're not going to do that. So we're going to go and we're going down to generate scene. So we're just going to draw these as color. So down here near the end, where the scene is just about done rendering, we're going to go ahead and start rendering the particles. So because of the fact that the particles aren't going to write depth values, we can't render the particles first and then render the scene on top. We have to make sure that the particles are rendered last. That's one of the downsides to not writing to the depth buffer, is that things will only really look right if the things that don't write to depth are rendered last, because then of course anything rendered after won't be blind to certain elements of the scene. So let's take our particle billboard program. Let's bind it. Billboard dot send uniform. We're going to set up our U texture with a value of 0. Then we're going to send our matrices, and that's all we need for this. Send mat4. In fact, we can really just copy these from here. I'm going to bring these down, and I'm going to change the name to billboard. Now the camera is going to be the same, but for the mat4, let's take the fog effect dot transform dot data. And so if you want to move this fog effect around or the sparkles around, you could change this transform and it will apply. So once we have that, we can actually just call fog effect dot render, and that'll do the trick. Then we can take our billboard and we can send the model matrix for the other effects. So let's change it this time to sparkle effect. Now, in the scope of this program, we're not actually moving these transforms, so it won't make a difference, but you know, for the sake of being complete, we take our sparkle effect and we render that sucker as well. And we finish off by if we look ahead a little bit here, we can unbind, instead of unbinding the static geometry shader, we can just call unbind on billboard, and looks good to me. So let's give this a run and see what the scene looks like now. So, no particles. That's a shame. Let's try and find out why, right? So let's see. Hey guys, I'm back. So, all of you are laughing pretty hard at me right now because you saw the problem a long time ago. So our alpha wasn't coming through and was multiplying everything by 0 because I made a mistake back in the vertex shader. I meant to set alpha equal to the incoming alpha, right? That's what it's for. So we want to grab our incoming alpha, bring it into here, and then we're good to go. Now if we run everything, we will find particles. So the smoke ones are taking a second to come up, but that's the intent, right? They're very subtle. With the texture on the ground being different, they'd probably look a bit better because they have kind of the same color. And you know what? If we're here, why not make that texture work better for this? So let's go for it. Let's go into our assets textures, change the ground real quick. Let's see, what do we want to do here? Let's bring the curves. Let's like bring down the green or something, or everything but the green. Let's make this all like swampy. Cool, it's all green now. Let's make it dark. Brightness down. Yeah, now look at that swamp. That's a swamp. Let's make it more swampy. Let's add something to noise. Want to add a little bit of noise? Sure. Yeah, noise. That's a swamp. Okay. What else? Let's make it a little. Ooh, let's add one of these. Ooh, that's cool. I don't know about you guys, but that is a swamp. Look at that. Neat swamp. Right. Let's save this. I am really sorry for all you artists right now that had to watch that. Let's run this again. There we go. So now the smoke particles on the ground are a little bit more noticeable, and it's a little bit more eerie, right? It's just kind of giving it that extra pop that something is happening. And if those particles were interacting with your player as you were to walk around, that would be pretty cool as well. And because the particle positions are still updated on the CPU, it's absolutely possible for you to do some basic collision checks and make the particles, react to that. We can see the sparkles coming up around the sword, and now that's kind of drawing your eyes there a little bit more, and it looks like something that you certainly want to go check out. Because these particles are being output to the same frame buffer that everything else is, the bloom will pick it up if the particle is bright enough or in such a location that it can pick up bloom. Let's take a look at the end site. I'm going to copy over the new texture to the location I have, the exe. Let's run this in end site. Let's check out what's happening. We've just kind of been playing around for the last little while, but that's fine. Then we'll take a look at the files and we're all good. So let's wait for some of these to be populated. Some of these particle effects to start up real nice. All of these facing the camera, of course, which is the whole point of the geometry shader. You can see here those sparkles are always facing us. Let's stop the frame here. Let's go back to the beginning. We have our clears, of course, these green lines. Then we have depth buffer coming through here. Then we have our color buffer with shadows still enabled. Then we have particles. Now, if I enable this wireframe view, you can see that there are a lot of particles, and each one of these was rendered as a single point. If we take a look at the bottom left here, where it shows us the draw call, they were rendered as points. They were literally rendered as points, yet we have quads because of the magic of the geometry shader. Next call as well, a lot fewer, maximum of 4, which is exactly what we're seeing here. That's perfect. We can see this one has become very small now. This one is still respecting the depth buffer because something's there, even though it's not writing to it, and that's perfect. We can see this one's popping out here a little bit. It's awesome stuff. And of course, all these quads, although different in size, have absolutely no perspective shift on them because all of the vertices are equally far away from the camera. They're all facing me perfectly. So with that, we get the high pass, which, look at this example, that's perfect. It's picking up a couple of those particles as well, being blurred a bunch, and then added back to the regular scene, and we have a little bit of glow there. Really cool stuff. So, add particles into your games. Also, it's one of the homework questions is to work with particles too. So now you have a good basis on which to do that. So let's take a look at the files, and then you're all free to go. We have our vertex shader for billboard, fragment shader for billboard, geometry shader for billboard. Let me try and get this all in one shot. There we go. Let's take a look at particle effect.h. This guy here we downloaded and made some changes to, mainly at the bottom. Particle effect.cpp, lots of changes here, added buffer offset, game.h, just included the file up here, and then created a new shader as well as a couple particle effects. Game.cpp, of course, experienced some more changes up here, loading the billboard. This is just the same old stuff from before. Same old buffers, but after which we have the effects updated in the update loop, and then past the compute shadow map with generate scene. At the bottom we have some additional calls, and the rest of the file remains unchanged. What else did we have? The shader program, right? Just one new function being added here, as well as the geometry shader handle. CPP saw the addition of a new function here, Very similar to the previous one. And the rest has not changed since the video for it. Hope you had some fun with this one. I certainly did. Go ahead and play around with some of these particle effects, add a whole bunch of new ones, make some textures, add them to your games, all of that fun stuff. That's all something you can do now, and you can add ridiculous amounts of these, right? Let's go crazy. For those of you still around, let's, add 50,000 particles, 100 per second. I have not tested this before. Let's see what happens. It won't break. That's what I hope will happen, because we took the time to write a proper particle system. Look at that. Look at that. It's running like there's no difference. That's amazing. 50,000 particles. Remember, this slight chug you're seeing here is just caused by my recording software. So if I wasn't recording, this would run 60 FPS. That's amazing. Look at that. Look at the effects we're getting here. Wow. That's crazy. Right? Modern OpenGL particle system right here. If that doesn't impress you, I don't know what will. Throw 100,000 particles at your game. Absolutely. Alright, I'll see you guys in class. Have a good week. Thanks for watching.